So welcome Level 3 physicists to our next lesson in NCEA Level 3 Mechanics, Rotational Inertia. So imagine throwing cats. So far we've talked, at least in Level 2 Physics, about objects moving without rotation. So now we're going to add in the concept of rotation. And we're going to use the concept of the centre of mass that we learnt earlier about. Okay, so consider throwing Albert the cat across the slide. So when we actually place a blue dot on Albert's centre of mass, as we see in the diagram below, and the red dot's going to be on Albert's tail, and we throw him again across the slide, you'll see every point of Albert will have a different equation of motion. Okay, and basically you'll see that his centre of mass looks a lot less complicated in terms of motion than on his tail. Okay, so Albert's known as an extended body, a non-rigid extended body, because he can change shape. Okay, he can roll into a ball, for example, because it's a cat. Whereas a wrench is a rigid extended body, because its shape does not change. And in Level 3, we tend to focus on rigid extended bodies because the physics is a little bit easier. Okay, and you can also move a wrench or translate it across the slide without rotating it. Okay, and this is essentially what we did in Level 2 Physics. Okay, so you'll note that at every point the wrench essentially has the same velocity. Okay, so you can basically say that every point on a rigid extended body moving across the page can be considered basically a single particle. So what we do, we look at mechanics in Level 2. However, you can also rotate the wrench. Okay, so the wrench can also be rotated around its centre of mass. Okay, and we've already learned earlier in circular motion, that means that the wrench has a different velocity, whether it be on the outside of the wrench or on the inside of the wrench. Okay, this is circular motion. Okay, and if we rotate and translate the wrench, we get the following transformation. So this is where the concept of torque comes in. So torque, or turning force, which you would have looked at Level 2, causes in circular motion an angular acceleration alpha. So again, when we're thinking about Albert the physics cat, we essentially made him rotate by applying a force or a moment of torque at a tangent to his tail. And this is analogous to the torque in translational motion, where torque equals the force times the distance. Okay, so torque in rotational motion has the same symbol, torr. The moment of inertia has capital I as a symbol, and the angular acceleration is alpha. And the units of torque are Newton meters, just as they were in translational motion. And the moment of inertia has the units of kilograms meters squared, and angular acceleration from circular motion has the units of radians per second Okay, so essentially, in order for angular acceleration to occur, the sum of the torques operating on a circular object or an object have to be greater than 0. So you've also got the concept of rotational kinetic energy. So if you consider two bowling balls on a table, okay, so if it's stationary, just staying there, the kinetic energy is equal to 0, but if it's rotating, then it's spinning in its place, then the kinetic energy is not going to be equal to 0. It will be in terms of translational motion, but in circular motion, it will not. Okay, so neither ball's rolling, so both have 0 translational kinetic energy, but the second ball, because it's spinning in its place, will have rotational kinetic energy. Okay, so the centre of mass of this bowling ball is going to stay where it is, but every particle which is not in the centre of mass will have its own tangential velocity, therefore its own kinetic energy. Okay, so in translation, every mass particle has the same velocity. It's not the case in rotational motion. Okay, each mass has a velocity that's proportional to how far away it is from the centre of mass, the radius, okay, as you can see from the diagram. So, because velocity equals radius times omega, the angular velocity, each particle in a rotating object will have a kinetic energy of half mv squared. So in this case, half mv r omega squared, or in summary, half mr squared omega squared. Okay, so given that omega is the same for all the particles in an object, which we learned earlier with circular motion, the total kinetic energy will be given the equation of half I omega squared, where I is this rotational inertia we'll explore in more detail, and that rotational inertia equals the sum of the masses times the radius squared for each particle from the centre of mass. So in terms of rotational inertia, every shape has its own rotational inertia, which you can see here. So for example, a hoop has a rotational inertia around mr squared, whereas something like a spherical shell has a rotational inertia of 2/3 mr squared. Okay, so you have to know all of these. And also you've got the idea that a thin rod around its end has a rotational inertia of 1/3 the mass times its length squared, or a slab around its centre is 1/12 the mass times the width squared plus the length squared. Okay, and again, you have to be aware of all these different rotational inertias for all shapes.